Water flows through a 2D diffuser having a 20-degree expansion angle, as shown in the figure. Assume the flow in the diffuser can be treated as a radial flow emanating from a source at the origin O. A. If the velocity at the entrance is 30 meters per second, determine the expression for the pressure gradient along the diffuser walls. And B. What is the pressure rise between the entrance and exit? So first and foremost, we want to define where the inlet and exit are. Those are going to be right here along the diffuser walls. We'll have the inlet, and then, oh, pardon for that T. The exit will be this big wide region. This will be the exit. All right. So first thing we want to do is we want to recognize that this is a source. We're using a 2D source flow. And so we're going to need the velocity field equation for a 2D source flow. And what that looks like is, and this is all for A, by the way, is this equation right here. I'm going to put it in blue so we especially don't forget it because we're going to be referencing it frequently. So we're going to have VR for V radius or radial at that radial position will be Q over 2 pi R, where Q is the strength of the source. And then R is the radial position. And so we see that R is actually over here. It's defined for us. And so we know where the radial distance is. The first thing we want to do is we want to define the strength of the source. And so since we have the inlet velocity given, we will reorganize this equation to be Q is equal to VR times 2 pi R at the inlet. And so what that turns out to be is we will have Q equal to 30 meters per second times 2 pi R, where R is set to be 2 meters. That's not 2m, that's 2 meters. And so if we solve this out, Q turns out to be 120 pi meters squared per second. So that's what Q is. We're going to need that. The next thing we want to do is we want to utilize the Bernoulli equation because obviously this is dissipating out. The Bernoulli equation maintains pressure. It is a conservation of pressure equation. And so that's going to be our next step. We're going to use the Bernoulli equation. And so this will be pretty direct. We're going to start with pressure plus 1/2 rho v squared is equal to a constant. We'll just leave it there. And then what we're going to do is we're going to derive this with respect to ddr. And so we're going to do ddr for this whole thing. And we're going to need to move this over to the side. So that's what this is going to be. And the expression we're going to get is we're going to have dp. I'm sorry, that's not white. We'll keep our colors consistent here. We're going to have dp dr is equal to negative 1/2 rho v squared, where this v is actually, this is going to be v radial. And all of this will be, again, derived with respect to ddr. And the reason there's no constant here is because you derive a constant, you get 0. And so we can just immediately take that out. It's as though we've already evaluated the derivative there. Evaluating this, we'll go one step further. dpdr is equal to negative rho vr times dvr dr. Remember the chain rule, and then we took the square down and got rid of the 1/2. And so that's the expression for dpdr. We need this expression, dvdr dr, in order to find a proper, pressure gradient expression. So what we're going to do is we're going to evaluate that right here. We'll just do it tiny over here, and we'll have this is actually equal to just negative q over 2 pi r squared. Reason being is if we come over here, we have this expression, which is what we are evaluating. And because r is on the bottom, when we derive it, it turns into a squared, and we pull the negative out. And with that, we can then do dpdr is equal to negative rho. VR is q over 2 pi r times this expression right here, which is negative q over 2 pi r squared. So we can then simplify all of this, and we'll get dp dr is equal to, it's not going to be negative because we have two negatives that cancel out. And so it's going to turn into rho q squared over 4 pi squared r to the cubed. And we can find a numerical solution for this because we know rho, we know the density of water, this is water flowing, and rho is equal to 999 kilograms per meter cubed. Q we've solved for, and Q is 120 pi meters squared per second. So we can plug all that in. We'll leave it in terms of R as a variable. And what we'll get is dp dr is equal to 999 kilograms per meter cubed times 120 pi meters squared per second, quantity squared. Then we'll get the 4 pi squared, and then it's all going to be with respect to r cubed. And so we can evaluate this, but I'm going to do that on the next sheet right here. And so what we get is, for our answer for A, and this is the final answer, is we will get dp dr is equal to 3.60 times 10 to the 6 over r cubed. And then those units are pascals per meter cubed. And so that's the answer. We'll box it in gold so we can really point that out and celebrate. And then it's time to move on to part B. And so B, again, is asking about the pressure loss from the inlet to the exit. So the first thing we need to do is, because we know this is going to follow Bernoulli's equation, we need to back that out, and we're going to say, okay, we need the exit velocity. So we have an expression for this. We can use the one we've been using, VR at the exit is equal to Q over 2 pi r at the exit. And so what we get is we'll plug in our values. We'll get VR exit is equal to 120 pi meters squared per second over 2 pi times 7 meters. 7 meters is the distance radially at which the exit of the diffuser takes place. And then if we solve for that, we will get 8.57 meters per second. And so what we're going to do is we're going to go back to the Bernoulli equation. And we're going to say the pressure difference, delta P, is simply equal to the difference in dynamic pressures, because that's all that's changing here. So we're going to have 1/2 rho VR at the inlet squared minus VR squared at the exit. So we plug in our numbers. We'll get delta P is equal to 1/2 999 kilograms per meter cubed. And we get the 30 meters per second quantity squared minus 8.57 meters per second quantity squared. And the final result should be 412 kilopascals. Let's confirm that once more. Yes. Is 412.852 kilopascals. Note I put this in kilopascals, and so if you were to solve this out, you would get it in pascals, and you get 412,000. But that is the answer for part B. And you can go on your merry way knowing how this diffuser works, assuming source flow.